Okay, so this is our project, and I'm gonna hand it off to Cynthia to do the introduction.
So our project is creating an AI to detect pneumonia. As a brief introduction to pneumonia, pneumonia is a lung infection that can be caused by bacteria, fungi, or viruses. It causes inflammation, buildup within the lungs, and some symptoms include cough, shortness of breath, chest pain, and difficult breathing. It can be fatal if left untreated, and it is treatable, and treatment is more successful if diagnosed early on. This means that diagnosing pneumonia early on is vital to the patient's well-being. Our project is to create an AI model that can accurately predict if a patient has pneumonia based on an X-ray of their lungs. The purpose of our project was to create an engine to improve the accuracy and efficiency of our diagnosis. Um, our models are given an X-ray image, which is then run on their network, and then the model outputs a number which represents its prediction on whether or not the patient has pneumonia.
All right, so diving into our data, we start with the data set of 2,400 chest X-ray images, each labeled as either pneumonia or healthy. The images were already pre-processed and resized to 64 by 64 pixels with three color channels, which made our job easier when feeding it into our models. Each one of the data set had three parts, where 1 equals pneumonia and 0 equals healthy, the split, trainer test, and the index for the image location. We were working with a balanced data set. Um, 1,200 pneumonia images and 1,200 healthy ones, which is super helpful for training a fair and unbiased model. Now, for the data split, we used the classic 80-20 split. So about 1,920 images were used for training and the remaining were reserved for testing. Both pneumonia and healthy images were evenly distributed in both the train and test sets, so there wasn't any imbalance affecting our outcomes. This balance was super important, especially in the medical field. We don't want models that are biased towards one diagnosis over the other. So going to our baseline models before jumping into fancy neural networks or transfer learning, it's like our first draft. So to get these working, we had to find the image data. Since the 3D arrays were in 64 by 64 by 3, we converted them into 1D arrays using NumPy. This process basically enrolls the images into a long vector of pixel values, which allows classic machine learning models like KNN, logistic regression trees, uh, logistic regression and decision trees to make predictions. Each model came with a couple of hyperparameters. For example, we set KNN to 5 neighbors, logistic regression to 1,000 max iterations, etc. Building these baseline models was a crucial step, not just to compare later results, but to understand the limitations of traditional methods in detecting medical conditions like pneumonia. Okay, Simran can go
So,
ahead.
yeah, so to move on to more complex models, we used neural networks. The proper definition is a machine learning model consisting of interconnected nodes called neurons that process information and make predictions. With that being said, this structure for an NN, which has inputs, hidden layers, and outputs. We used two new activation functions. These were called ReLU and softmax, which in the end should calculate a probability for a diagnosis. Since neural networks can be useful for a wide variety of tasks, while CNNs include convolutional layers before the neural network, which help with the feature extraction and enhancing what we're feeding into the neural network. On the graphs themselves, we have training and validation data, a line that represents chance. The green shows the best epoch, which varies for each graph. For the dense, we had flattened image data with two hidden layers and many neurons using ReLU. And we had two neurons for classification using softmax. The CNN model had convolutional layers, a dense layer using ReLU, and then an output layer of two neurons using softmax once again. We all used 100 epochs for each model too.
Okay. Um, okay, moving on to transfer learning. Up until this point, we had trained our own models like CNNs and dense networks, and they worked pretty well, but we wanted to go further. And that's where transfer learning comes in. Instead of starting from scratch, we used pre-trained models like VGG16, VGG19, ResNet 50, etc. Basically, models that already understand how to see from being trained on millions of images. We fine-tuned them for pneumonia detection. We tested several of these models, and the results were more impressive compared to our earlier ones. So before we go into what the findings were from these models, I'm just going to explain what the sections of the graph mean. So the true positive means that the model correctly predicted someone had pneumonia. The true negative means that the model correctly predicted someone was healthy. False positive means when the model thinks someone has pneumonia but they actually don't. And false negative is when the model says someone is healthy but they actually have pneumonia. So now looking at the table of results, our best performing model was VGG19. It had a strong balance of catching the most pneumonia cases and not flagging too many healthy people. It also had a relatively low false negative, which is really important in medicine. And VGG16 performed decently too, just a little less accurate than the other three. Um, but still perform but still performing better than CNN networks and dense. DenseNet performed well as well, but our ResNet 50, while really aggressive in catching pneumonia, flagged way too many healthy people sick, which is why it had a super high false positive rate, which is just not ideal.
So moving on to metrics. Considering all the models used, metrics are valuable in determining the efficiency for our models to diagnose patients. The three metrics you must take into consideration are accuracy, precision, and recall. Accuracy is the ones we all already know. It tells us how often the model correctly predicts pneumonia and non-pneumonia cases. Next, precision tells us the proportion of predicted pneumonia cases that are actually pneumonia. High precision means fewer false alarms, which means fewer healthy patients are wrongly told that they might have pneumonia, reducing stress, unnecessary tests, and costs. Recall is the proportion of actual pneumonia cases that the model correctly identified. High recall is critical in medicine because we don't want to miss any real pneumonia cases. A low recall means that some patients with pneumonia go undetected, which could be life-threatening if untreated.
The table shows the best models that each of us were able to create. For each one of them, we measured the accuracy, precision, and recall. If we were ranking those models by accuracy, the last CNN model would be the champion. Similarly, the same model stands out in precision. However, as Cynthia mentioned earlier, recall is the best metric to use for detecting pneumonia, and in this case, we have two models that have a similar higher percentage, around 97%, which are the transfer learning model VGG16 and the first CNN model. 97% is not bad at all, and I'm sure they could be even better if we had more time to work on their hyperparameters.
Excuse me. To respect all of our time, can you guys please start wrapping up?
Yeah, we're almost done.
Data augmentation is our next topic. So it is adding additional data onto the training set of a model where the additional data is different in some ways compared to the previous data, like rotated, scaled up and down, or colored differently. The purpose of diversifying the input data is to train our models to handle a larger range of inputs and therefore produce more accurate outputs. Our models perform pretty well when tested on our test data, but that's because the test data looked really similar to our training data, and when we use field data, it didn't look like what our data was tested on, and it produced less accurate results. In the real world, certain models might perform worse than when x-rays from different hospitals are used, because those x-rays look different than the model that it was trained on. That's important. That's why data augmentation is important, because it produces accurate results from all different types of inputs.
So in conclusion, VGG16 and VGG19 stand out as the most effective models for pneumonia detection. While all models aim for accuracy, recall is especially critical in a medical context to avoid misdiagnoses. The high and consistent recall and accuracy of these transfer models make them more reliable than RCNNs, despite occasional false positives. Prioritizing recalls help ensure sick patients are identified, reducing health risks. Overall, VGG16 and VGG19 are the most clinically reliable options, offering strong diagnostic performance and better health outcomes at scale.
That's
Thank you.
yeah, that's
Cool.
all.
Thank you, Stacked. Yeah, I really like the metrics that you guys presented. I think for any of the other teams that's like watching you guys today,